This is the 2024 deferred paper. It's paper 2 and we're on section B. It's the last question on the paper, question 10, and it's a question on trigonometry. So we've got, so it's about a bike, and we've got to imagine a small nail getting stuck in the tyre of the bike. And Chloe, who's cycling the bike, she keeps cycling at the same speed, and the nail is stuck on the front wheel. And they give us an equation which describes the height of the nail as it's going. If you just get the height as a function of time of the nail as it's going on its journey, this is the function that describes it. So the first thing we're asked to do is to complete the table below. Now, in anything in bold, always pay attention. Everything's in radians here. So you must set your calculator to radians. We're going to just put in this function into the calculator. So what you do on your calculator is two things. You set it to radians, and then you use the fx function on your calculator, and you type in this function exactly as it is with the brackets, etc. And you get the values of the function, then you do a table you put in from 0 to 0.8, and you go up in steps of 0.1. If you do that on the calculator, these are the values you get for the height. So what we're saying is, when you turn on your stopwatch, after 0 seconds, the height of the nail is at 0. After 0.1 seconds, the height is 30, and the height is in centimeters, it says here, etc. This one's already filled in. After 0.2 seconds, the height of the nail is 60 centimeters. So as I said, two things: set your calculator to radians and use the fx function on your calculator. Now you have the values. The next thing is to plot them. And if you plot those points, so these are your points for your graph. 0, 0 is the first point, 0.130, etc. So there's 0.130. You get these points here, 1, 2, 3, these points. You see the points here. Now, before I joined them, it wasn't obvious what kind of a shape it was. If I had actually joined the points as they are, they'd make a straight line, a kind of a zigzag shape if you join them. This is where your knowledge of trigonometry is expected. You're expected to know that a trigonometric function, which this is, it's a cos, is a kind of a wave shape function. So just be aware of that. So it's so if you know it's a wave function, you're going to get that kind of a graph. Now, just something to notice before we move on to the next part of the question. You can see the period where it starts repeating itself is 0.4. Every 0.4 of a second it repeats itself, and then again after another 0.4 up to 0.8. So this is the nail going up and down. So the nail starts at 0, and it reaches this height here, back down here, as the wheel is rotating. We're told the period of the graph ht, or the function ht, is 0.4. What does period mean? As we just explained, that's where it repeats itself, where it starts going around again. So in our case, that means the wheel has done a full rotation and the nail is back to where it started. The radius of the wheel is 30 centimeters. Work out the distance travelled in one full revolution. So what they're really asking there is, what's the circumference of the circle? That the wheel makes. So, and that's 2 pi r. So 2 pi r, and the radius is 30. So you get in centimeters. Be careful here now. I have a warning here about units again. They're mixing up units. Watch out for that. Centimeters and millimeters. So we're right now we're in centimeters, but they want the answer in millimeters. So you convert that to millimeters. And basically you multiply by 10, and when you work it out to the nearest millimeter, you get 1885. Now, using your answer to C part I, so we're going to work out the speed that she's cycling at. So first and foremost, speed is distance over time. So we're going to come to that in a minute. First of all, though, we have the distance she travels in one full revolution. We know that the distance, we just worked it out there to be 1885 millimeters. We also know the time it takes to do one full revolution. Well, actually, it's 0.4 there. So if we come down here, we can now get the speed is distance over time. So the period, as we just saw earlier, every 0.4 seconds repeats itself, the graph. We also know that in that time, we just worked out it has covered 1885 millimeters. So just speed is distance over time. However, there's another complication with units here. We want the answer in kilometers per hour. So I would put in the units in my equation of distance over time to keep track of them basically, and then change them one by one as we're going through it. We want kilometers per hour, so what's millimeters in kilometers is what we're really asking, I suppose. So you got to come over here, think of a millimeter as a thousandth of a kilometer, or 10 to the power minus 3, same thing. And a millimeter is a thousandth of a meter. So altogether, a millimeter is 1 millionth, or 10 to the power minus 6 of a kilometer. So to convert millimeters to kilometers, you just need a millionth, basically, and now it's in kilometers. Same idea with time. We have to go from seconds, it has to be per hour. So to convert seconds to hours, you divide by 60 by 60, which is 3,600. And you finally have your answer in kilometers per hours. And on the calculator, if you work it out, it turns out to be 17 kilometers per hour to the nearest kilometer. Finally, the last part of the question, part D, is a 3D problem. And there's a fixed method for these. You try and spot 2D shapes in the 3D object. So for example, there's a triangle. We might need to use that, or maybe not, but just identify them anyway. There's one triangle. Another one here. This triangle here. And we're going to see later that this triangle becomes important, the one on the base, on the ground, A to B to 0. Okay. Now, things to spot as well is, it might not look like it on a 2D diagram, but that's basically a right angle there. If you can see, if you could see that in 3D, that's a right angle, because this is along the ground and that's a vertical. We were told that OB is along the ground, so you have to imagine that's actually a right angled triangle as well. And indeed, that's the first one we look at. This triangle here, OB, and up to the height. We're talking about a building basically. This is the top of the building up here. So if you take just that triangle as a 2D object, it's OB along the base, the height H, and we join here to here. We're asked for a formula for OB along the ground here, and the trick here is to work with what you're given. We're given this angle of elevation, as it's called. The angle looking up is the angle of elevation always. That's 30. And if you look at 30, we're looking for this along here. We have this H. What joins all those three things together? The angle, the opposite, and the adjacent. Opposite and adjacent should remind us to use tan. So the tan of 30 is H over the bit we're looking for, which is OB. In the tables, that's a special angle. 1 over root 3 is equal to H over OB. And we can now rearrange the formula, and basically OB by 1 is root 3 by H. So we have what we were asked for, OB in terms of H. So there's a H left there still. So we now know that that's H root 3. So that's the first, in these 3D questions, there's fixed techniques you can use. The first technique, as I said, is break it down into 2D shapes. The second part of the method is to actually link that shape together now with the next shape, the next 2D shape. So use some side they have in common or some angle. So we're going to reuse and recycle the OB now in the next diagram. So just keep an eye out for that. We're told the distance along the ground is 120 from A to B. 120. So if you're told that distance, that brings, I suppose, into our focus this triangle here. This 2D shape here. So we're going to draw that and put down what we know. So here we have it, A, B, and O. And that's 120. And we're going to reuse and recycle, as I said. So that OB is the same as that OB there. And we're going to H root 3, put that down there. We're also told in the question that AO is H. So because it's 45 degrees here and here, so these two sides are the same, so isosceles, so that's H and that's H. So we can now put in AO as H as well. And one last detail we're given is that the angle is 60. Sorry, we're given that down here actually. The angle AOB is 60, AOB, so that's 60 in there. Now taking all this together, what have we got? We're looking for H. We want a formula with h in it. And we want to use, obviously all of these need to be used, they wouldn't be given to us otherwise. So we need a formula that ties all these things together. What ties that side, that side, that side, and that angle together? The only thing that ties them all together is the cosine rule. If you write down the cosine rule from the tables, or look at it visually, what's it saying is any side squared is the other two sides squared minus 2 times the other two sides by the cos of the angle in between. So we'll take that. Any side squared, 120 squared, is the other two sides squared. That squared plus that squared, so that's here. Minus 2 times the two sides, that, by the cos of the angle in between, which in this case is 60. And you can work out that then. H squared, that's h root 3 in a bracket to be squared. You get h squared by 3. Over here, we've got cos 60 in the tables as a half. It's a special angle. You've got h by h is h squared, etc. You tidy it all up, and you get h squared, and 3h squared is 4h squared. The 2's cancel here. You get root 3h squared. Now, h squared is common to both terms here. We can take it inside the bracket. 4 minus root 3. Divide across by 4 minus root 3 to get h squared on its own. And finally, h is the square root of your answer. Put all this into the calculator, get the square root, and you'll end up with the answer. The height is 79.7 meters. And that's the end of the question.